Meet Leonard, the butterfly curve. He's not like other graphs. Most graphs prefer the Cartesian plane, but not Leonard. He is a polar curve and is located on the polar plane. You're probably wondering how Leonard got here. So are we. Let's get into it.
A Cartesian plane is a system that uses horizontal and vertical x and y axes. Points using x and y show the distance between the origin on perpendicular lines. A polar plane is a system that is two-dimensional. Its points are given by angles and the distance from the central point, which is called the pole. Since it has the ability to show angles, it is used by engineers and physicists because it makes equations simpler. It is a great plane to use for navigation. Here's a simple linear function on a Cartesian plane. Here's a basic example on a polar plane. You are able to convert a Cartesian point to create a polar point by using this conversion. For example, point 1, 2 can be turned into this.
As we just learned, polar points are used to describe paths which are an absolute distance from a specific point, the pole. Each point is given by r, theta, where r is the distance from the pole at the center, and theta is a counterclockwise angle between the point, pole, and horizontal axis. We can form polar equations to describe relationships between r and theta. There are limitless different polar curves, many of which are very similar to graphs we are already familiar with. For example, you can make a line or circle. Some other polar curves include limicons, rose curves, and spirals. More complicated equations can create stunning visuals, such as the butterfly curve.
So what we have here is Leonard the butterfly's curve's polar equation on the top left. In this section of the video, let's break this equation down. Starting with e to the power of sine theta, we can see that it changes the distance from the origin. So look at this slider. It changes the amount of times that it's being repeated. Next, let's move on to -2 cosine 4 theta. Do you guys remember what the negative sign does to the transformation of a function? You better. We learned this. I'm sure a lot of you are thinking that the negative sign causes the graph to flip. In this equation, however, the negative sign actually makes the bigger wings shrink and the smaller wings grow larger. Let me show you what I mean by this. This one has the +2 instead of the -2. And we can see that the smaller wing here actually becomes bigger, and the larger wing here becomes smaller. Next, we move on to 4 theta. It forms the 4 wings of Leonard. It actually has a pretty interesting pattern. The number here correlates with the number of wings that are on display right now. For example, if we plug in a different number, for example 3, we get 3 wings. Now 5, we get 5 wings. And 6, we got 6 wings. There's also a hidden pattern. Do you see it? That's right. Even numbers have smaller wings between the larger ones, while odd numbers don't. For example, 6 is an even number and has a smaller wing between the 2 larger wings. And of course, our special little Leonard is even, so he has a little smaller wing between the 2 larger wings on either side. We can also plug in a bigger number like 20. Since 20 is even, it'll have a smaller wing between the 2 larger wings. So even with larger numbers, it still follows the pattern. Lastly, we have this term right over here. It was only added for aesthetic reasons, to make the graph look fuller and more aesthetically pleasing by repeating the lines of the butterfly. To illustrate, this purple line doesn't have the sine function. Look at how simple and boring it is. See the difference? Lastly, there are 2 significant properties we can deduce. The first is that the curve R is symmetric, and that it's reflecting across the y-axis. The second is that the wings and body have 12 stripes. For example, 1, 2, 3, 4, 5, 6, 7, 8, 9, etc.
To start the building process, we first gathered our materials. We got a wood backing to act as our polar plane and wire to form the graph. Screws would act as points, and string would help us see the angles. After seeing the polar plane on the wood, we inserted some screws to act as example points. Then, using the plane as a reference, we created the graph by bending the wire. One challenge we ran into was making sure that our graph and the proportions of the plane were mathematically accurate.
It took some time, but overall we were satisfied with our end result, and so was Leonard.
So now we know. Polar graphs might seem complicated, but they're really quite simple. So the next time you see a butterfly, you'll also think of math. You're welcome.